Greetings 2021ers, this is Professor Kaufman, and this video will survey what you're up against for Project 2. You can tell by looking at the specification for the project over here that there are only two problems this time, and most students find this to be a somewhat easier project than its predecessor in Project 1. The first thing that I'll do while I'm pulling this up is to get a copy of the code pack for the project. I could right-click and save or click on this thing. Instead, since I want to do this perhaps on a remote machine using the terminal, I'm actually going to copy the link address down over here and buzz over to my terminal here. And I'm going to issue a wget command. This is available on most Linux systems, probably other Unix systems as well. We'll retrieve something from the web. All I need is a web address, and so I'll paste in Control-Shift-V on a lot of terminal settings. The web link over there, I'll wget that thing, and if I ls at this point, I should have that p2code.zip. I'll issue the unzip command to create this p2 code directory, change in there, and I should be then in good shape to have the code pack and its contents available. As usual, we'll have a makefile, and so making use of the build system that's provided there will ease your development. And should you ever forget what the makefile can do for you, type make help, and it'll print out a little help message about how to run tests associated with a problem or a specific test, how to run all tests, create zips, etc., and so forth. So let's turn our attention over to the spec here and just take a brief tour. As usual, will be a trusting regime, and you'll earn quite a bit of credit for that here. The manual inspection is somewhat less. Let's survey instead over here the project's files, which are somewhat smaller in quantity than the previous project. There's the makefile, and then a bunch of files associated with problem 1, which will sort of round around a simulated battery meter of sorts. This will get you doing some bitwise operations. And then just a couple files for problem 2, as you won't be writing code there. Instead, you'll be doing some debugging in it, mainly in this puzzlebox.c file, and editing an input.txt to try to get inputs associated with that. Let's take those two problems in turn. So the battery simulator puts you in a position wherein you are going to work with a pretend machine. You don't quite have the budget to create an actual embedded device where you could run your C code to get real hardware and so forth, but we can emulate that and provide a little simulator, which is oftentimes what you do in a testing scenario anyway. And the little machine that we're going to simulate is something that you could plug into a small device, perhaps a phone or something like that. And it measures the voltage coming off of a battery. And the voltage translates into how much charge remains in the battery. So in this little device, there'll be a sensor. The sensor is connected to the processor in some way and gives a reading. And this is not a direct, it's a direct reading on the voltage, but has to have some conversions done to it. That meter, that measure of the sensor value, is mapped to something called a port, usually some connections into the processor, and presented in a C program as a global variable. The global variable is called this bat voltage port here. And you can see it's a 16-bit value, a short, and has some features to it where this is oftentimes the case with sensors. The raw value that it provides is in a slightly weird unit. It measures things in 1/2 millivolts, so 0.0005 volts. This will require you then to do a little bit of conversion. The idea here then is to take that value, to do some transformations on it to calculate a voltage and then a percentage full for the battery, and then to display this in some sort of compelling fashion by populating some LCD panels that are attached to another part of this simulated processor. So we'll come back to this chart in just a second, but I think a good way to sort of recognize this is as follows. Your ultimate goal is to create a little display that looks something like this, where this thing reads 49% at the moment. And then there's attached to it on this display a little visual indicator that has 2 bars on it, indicating that we're getting down there in terms of the battery stuff. There's a little percent indicator indicating that the number here, 49, is displaying a percentage. But you can also press a button on this little device that we're imagining to change this into voltage mode, which instead would display something like 4.23 volts, which, according to the little chart we'll look at in a second, is at full capacity, so at 100% charge right now. There are a bunch of examples further, and we'll return to this diagram in a second. But all this stuff then is managed. There's a little screen, there's a little sensor, and a few other oddities that are managed by some processor, typical of an embedded programming process. So first, let's talk for a second. You've got this little voltage port, and it's measuring some quantity on it. There's a relationship that's just about linear for lots of batteries, that if they're fully charged, then they'll have a high voltage. But as you execute the chemistry on that to get you sort of currents to flow through it, then gradually that voltage diminishes in an almost linear fashion over here, to the point that you get a lower voltage, a lower potential. And if you were to continue to sort of cycle through the chemistry of that stuff to try to get more currents, eventually this will damage the battery and it'll become unusable. So usually folks bow out at about 3 volts. They say the battery circuitry should say, like, stop drawing charge from it, otherwise you'll wreck your battery. And so this is the sort of general relation. At 3.8 volts, we're at 100% charge, fully charged. Anything above that is considered fully charged, and we'll quickly diminish down to it. And then as you execute the processor and whatever device is attached to it, that voltage will gradually diminish. Now the meter itself kicks out these half millivolts. So you can think of, like, oh, if the sensor value is 7600, you need to divide that in half, and that would be 3800 millivolts, or 3.0 volts. That's full charge over here. If instead the voltage was only 7,000, the sensor said 7,000, have that for 3,500, and that's 3.5 volts, you'd be somewhere in the middle over here. And if it gets down to a sensor value of 6,000, this is at 6 volts, this is just about dead at that point, and the circuitry will turn off the battery at that stage. So there's a little bit of math involved here, that to calculate whatever the voltage actually is, you have to take the port and divide it by 2. And there's a relationship then of the voltage to the percentage full over here. That's something like the following, that if you knocked 3,000 off the millivolts that are in there, and then divide by 8, because this is a range of 800 millivolts from empty to full, then you'd have yourself a percentage calculation. This then more or less comprises the first part of this, where you're going to be doing a little bit of a conversion. And I should jump down just quickly to the first function that you have to write. It's called set bat from ports. It will ask you to populate a little struct here called just bat t, I'll call bat, and do so by reading from some of the ports and figuring out then what the voltage should be, what the percentage is according to that, and a few other things. One final note, to determine whether or not you should display this information in millivolts or as a percentage, there's another port that we'll look at in a second. So you set the mode as either I'm displaying this in volts or I'm displaying it in percent. I think percent is the default. So let's have a look quick then at the next part of the machine to look at. It's called this bat status port. This has got a little bit of circuitry in it and is presented again as a C global variable called bat status port. Bit 4 in this character, 8 bits there to indicate different status features of the machine. Bit 4 indicates whether or not you should display things in volts or in percentage. So if that bit number 4 is 0, then you should show things in volts. Otherwise, you should show it in as a percentage. So only bit 4 matters in here, and you should generally just read this port as in trying to access the values that are in it, not put anything in this battery status port. So during the execution of this function that's mentioned down here, this set bat from ports, you'll want to look at those two global variables, the bat voltage port and bat status port, do some calculations to figure out what's my percentage what's my millivolts and my percentage from the bat voltage port, and also then check whether or not the display that's requested based on this button pushing, either a 1 or a 0 bit 4 in bat status port, whether or not that should put it in a correct mode associated. The struct itself is really simple, so refer to documentation here or in the header for that. There are a few constraints as you would write this first function. That first, this will be a small embedded processor, so it's not as fully featured as the kinds of processors that you have in your laptop or desktop computer. For instance, it does not have any floating point operations available in it. You'll have to do everything using an integer arithmetic. This isn't too hard as long as you're doing things like adding and subtracting with just integer values. C will automatically generate low-level instructions to do those. But as we're discussing in lecture, there's a big difference between the integer operations and the floating point operations, which operate with a different interpretation of the bits for those numbers. The other thing that you'll want to do is to try to avoid using division directly here. And this is because division as an instruction is a pretty slow instruction, as we've talked about during lecture. Instead, if you can, substitute instead of a division, a shift operation. And you recall from lecture that shifting by some number of bits is like dividing by some power of 2. And this is a good spot to employ those techniques because your code will run faster and be overall simpler. Finally, this is a sort of leading constraint. Try to make your code as simple as possible. For instance, avoid using nested conditionals. The reason for this is that we will eventually take the code that we're writing in C right now and rewrite it by hand in assembly for the subsequent project, project 3. This is made much easier if you have a pretty straightforward roadmap laid out in your C code, as it takes oftentimes several lines of assembly and a lot of pain and grit to do the same sorts of tasks that one line of C code might do. If your code gets much longer than 40 lines for this function, then you may get penalized for being overly complex. So that's your first function. I should mention where we're writing it. It's in, as the overview states, a single C file that you'll need to create called batupdate.c. Now that part is relatively short, like the sort of parsing a couple global variables and setting some values in a struct. Now comes the fun part. So the display for this thing is controlled by a single global variable as well. I think it's mentioned up here. It's called a bat display port. Unlike the other two, you should actually write things into this, so eventually set this global variable to be something. Each bit in this bat display port corresponds to turning something on in the display. And hopefully you've seen little LCD displays like this where there's like sort of blank panels that eventually could potentially turn on. So to get the shape of 4 here, I need to turn on this panel, and this panel, and this panel, and this panel. And each of these here is tied to a specific bit in this global variable, bat display port. 32 total bits because it's an integer. So for instance, in the middle here, if I wanted to turn on this little panel here, that's the upper right part of the middle digit, that corresponds to bit 11. And you can see in the global variable here, there's a 1 there. Versus there's a 0 and 10, so this little panel right here is turned off. Now there's rhyme or reason to this stuff, but first it's just good to appreciate that this diagram lays out some details that are somewhat good to internalize. For instance, over here, the first 3 bits, they correspond to little icons that turn on for voltage, for percent, so that's the 0th and the 1th. And then this arrow comes over here that the second bit over here turns on and off this little decimal place that's over here. And then the remaining digits over here, bits over here, they correspond to the 3 digits. So there's 7 panels here, 7 panels here, and 7 panels here. And this thing continues on so that bit 24 over here controls the lowest bar of the battery meter, and then you work your way up along these ways. So if I wanted full charge, I'd turn all of these bits 24, 25, 26, 27, 28 on. But since I have only a sort of a partial charge right now, I'd only turn the couple on. The numbers over here indicate the ranges, that if you're at between 5 and 29%, then you should turn on only the first bar. But if you're between 30 and 49%, then you should turn on both the first bar and the second bar. And you can see that we're at 49% right here, so turn on those two bars. If we charged up and got to 50, then both this number and this little bar indicator would go up by a little bit. Similarly, so over here, the voltages should be displayed, although you'll need to know the percent in order to determine what the level indicator over here should read as. Now, the process of laying out the bits for this thing involves some bitwise operations and some shifts and so forth. It's a good idea to wrap your head around, okay, these are the bit ranges, like 3 to 9 is this rightmost digits, 10 to 16 is this middle digits, 17 to 23 is this leftmost digits, and then there's a few oddities like the indicators over here. Now, how would you sort of get something like this? The 9, the 4, etc., the blank. There's a very regular pattern to this that's laid out in the next diagram down, that each digit comprised just of a bit pattern. So over here is how you would draw 0 by turning on the outer sequence of panels along here. You can see it follows a pattern. It's like starting with the top bit, then we go clockwise around with the last bit being the middle panel over here. And the patterns that are shown up here just display the bit patterns associated with drawing each of these digits. Now, it should be pretty obvious that this is not the bitwise representation for 0 internally, that there's a whole bunch of ones in here, and you know that integer 0 is all zeros in that respect. Instead, this is another way of saying, like, oh, for this interpretation, it's like a display of some kind, and so it's a bit pattern that corresponds to drawing in some fashion. To that end, it's a good idea to create an array that looks like this, where the 0th entry is a bit pattern that looks like this, and the 1th entry is a bit pattern that looks like this. It's not the number 1, but at the 1th entry is this 0000110, and that would, if plopped down at the right spot, display a 1 in the display that's over there. So too for 2, 3, 4, 5, and a few other things. Sometimes you do versions of this wherein you need a negative sign. But at any rate, this is a good thing to encode an array, because eventually if you figure out, oh, what I need is a 78 over here, what you can do is go to the 7th entry of the array and fish out a bit pattern. It should be this one. It's not well, actually it turns out to be the number 7 in binary as well, but that's an artifact. Over here, for instance, at the 8th entry would be this pattern, which is definitely not binary 8. But this would allow you to say, okay, here's the bit pair I want. Now I just have to get it to some spot. And typically then this global variable over here, which is going to control the display, can be constructed by taking the bit pattern for 8 and shifting it over a little bit, and then combining it with that global variable, oftentimes through a bitwise OR. So you OR these ones on over here. And then later on you shift this pattern for 7 over a little farther, OR it on, and now you've got a bunch of zeros, but some ones here and some ones here, so that when this thing displays, you see a 7, 8 over here. There's some description later on in writing those functions. For instance, in the second function called setDisplay from bat down here, which is responsible for taking one of these bat structures and then constructing this display variable so that it has a bit pattern to display the level indicators, the different digits, and so forth. And it involves quite a bit of shifting and ORing. There's some details of that stuff and some tips on how to go about doing this over here. This will take some amount of work, but we'll teach you a bunch of techniques and present one of the interesting use cases for those bitwise operations that we have discussed during lecture. Finally, then, there is a sort of overall update function, which is extremely easy to write. It's only 4 or 5 lines of code that calls first this set bat from ports and then the set display from bat. So long as those two succeed, then all's well. I think a good way to get started in this respect is just to lay out these 3 functions in the sort of source file that you have to create called batupdate.c, and then you can start running the tests associated with this. So let me do that quickly here. I'm going to come over here. I'll just fire up nano, and this has got to be a file called batupdate.c. And then I'm just going to copy some things here. Here's bat update over here. I'll paste that in here. And then over here, I'll grab this next one, bat display copy that, paste it in, and then go up here for one more, and then up here, got this guy. And then we should be good. Okay, so that lays out the prototypes that I'll need, along with documentation that I might find useful later. It'd be a good idea to pound include the bat.h header file that's in here. I'll save that thing. And all I'm going to do at this stage is over here, return 0. This is not going to do at all what the function is supposed to, but it will allow me to compile and run this. I'll page down a little ways. Similarly over here, I will return 0. That's good enough for now. And then down here for bat update, it's all supposed to return an int, return 0. Save that. Okay, now we should be pretty good to go. Those are the only 3 required functions. They certainly do not operate yet, but this should put me in a position to be able to compile and run code. Let's see, I'll have to exit out of this. I should, at this stage, be able to type make prob1 in order to build the problem1 stuff. Oh, but I forgot a semicolon here. So let me open that bat update. Let's see, Vim this time, because it lets me jump to a specific line number. Oh, rats. If I knew how to Vim, it probably would. I just need to, let's see, append semicolon there. Save and get out of that, and make prob1. Okay, we're good to go. Now, the primary thing that we're going to use to test this is to simulate this little machine. And for that, there's a little bat main that is presented over here. You can run that yourself. It's also run as part of the test cases. It takes a couple arguments. First, what you want to put on that little sensor value for the voltage. So here's bat main. For instance, I could put it at like 70, let's see, 7,200, for instance. And I have to indicate whether I want a voltage or a percent display. Let's start with a percent display to see how things go. Now you can see over here that this prints out several pieces of information. For instance, 7200 is the voltage port. The bat status port was set to OX91. There's a 1 set in there somewhere in those 8 bits to indicate percentage-wise. And then the simulator will sort of show me what the results of each of my function calls are. Set bat from ports over here, return to 0 as indicated, but didn't actually set anything properly. And then I call the simulator sets set display from bat over here and doesn't actually set any bits, so that's not too bad. And then eventually it'll display like this is what my display actually looks like, and nothing is displayed over here. Now, we can do something else here. For instance, if I modify my code just a little bit, here's bat update.c again. Actually, I'll fire up Vim for this because I want to be able to move around a little bit more, not a visual block. But I'll zip down here and do something like, oh, let's see, not here, but set this display equal to -1. Now, if you recall, -1 in binary is all ones. And so this is going to, within this display variable that I'm responsible for setting up, set the whole display to turn everything on at once. Also incorrect, but worth a sort of look at what effect that will have. Zip out of Vim here. I'll remake at this point and then run this bat simulator again. And shoot, okay, I thought this was going to turn everything on, but I guess I was wrong. Hang on a second, I'm going to pause for a second and figure out what I did wrong here. All right, that was embarrassing. It turns out I didn't save the file, so I was just recompiling everything. Forget to do that in Vim, so I think we should be in better shape now. If I, let's see, make prob1 now, prob1 now, we'll get a recompile. And now when I would run this thing, see all ones over here, but bat update hasn't done its thing yet. So let me instead make one more change, bring back Vim here, and down here, may as well pass in here. Let's see, call, let's see, set. Oh, I'll just do it here. What is it? Bat display port equals -1. And then if I remake that and run it now, then everything gets turned on. So this is undesirable, but shows you like, oh, once this global variable gets set, and oftentimes it'll be set based on what this set of values is, then some things in this simulated battery display turn on. In this case, since it's all ones, like everything gets turned on. In most cases, you won't want voltage and percentage to be on at the same time, that it's one or the other. And unless you happen to have 8.88 volts, which is nigh impossible in this case, you'll want to just selectively display stuff over here. The groupings of bits over here are meant to help you to identify. The first 3 bits have to do with voltage, percentage, and decimal. And over here, these are for this rightmost digit, the middle digit, the left digit, and this is the battery level indicator over here. And the top 3 bits aren't actually used for anything, so should oftentimes be 0 there. So that should give you some idea of where to get started by way of getting to work on this thing. Consult the documentation and proceed. We'll now turn our attention to problem 2, which is entirely different in nature, as it won't have you writing any code, but instead will have you working through a sort of puzzle. This is encoded in the puzzlebox.c file, and I think I've built it already over here, so you can see this puzzle box is built right over here, and you have access to the source code for this. Now, I'll state this up front. The intent here is to get you acquainted with using GDB, the GNU debugger. Debuggers are a general class of tools that allow you to stop time in a program and inspect what is happening in it. The central theme here is that this puzzle box takes as its input some input file, like what would come out of input.txt, and if it likes what it sees in the input, then it will award you some points. You can simply run it by saying puzzle box, then I'll feed it the input.txt over here. And you can see a couple things, probably the most pertinent being I didn't earn any points for this. But we'll have a look at why and how to improve matters in just a moment. Part of what's in the input.txt is your X500. And this will be unique to you. And it's used to generate a hash value, a random number that's sort of some amalgamation that's calculated from the string version of your X500. And this will give you some unique random values that mean your answers for the puzzle box won't necessarily be the same as what your neighbor's answers are. And to that end, it's much easier to sort of collaborate in various ways on a puzzle box because there isn't much risk of you inadvertently, giving away answers, because if you give your friend answers, they won't work for your friend's X500. So the first thing that I'll want to do is to open up that input.txt and enter my actual X500. Let's see. I'll enter my old student one, and that was cough0095, and I'll keep this 123 here for the moment. I'll write that thing. And if I rerun Puzzlebox at this point, I still don't get any points. And don't be disturbed that this will be capitalized each time. So at this stage, you might sort of wonder, like, what the hell should I do? And I could probably look at the Puzzlebox itself, the source code for it, to have a look. There's a considerable amount of stuff here. A lot of it is sort of set up. But you can see within the main, you'll see a sequence of calls to phase 1, phase 2, phase 3, etc. And each of these are tiny little source code puzzles that you'll want to make use of the debugger to solve. If I jump down here to phase 1, you can have a look at what we're up against. After all the signal handler settings and so forth, here's phase 1. The difference is that some inputs will be read out of the input file. So 3 in this case, and A, B, and C as they're assigned. And the A to I here, a string to integer or character data to integer, indicates that what's expected is some sort of a number at that stage. And you can see over here, whatever number I enter first, A, it has something added onto it that is randomized based on the hash. So whatever your hash value is, mod 41, that'll be added on. And then it'll look to see if A is less than B, and B is greater than C, and A is less than C. So there's sort of a relationship there between those. Now, if you're like me, let me jump back out to the shell over here. You can see, here's my hash value. I can't calculate modulo 41 in my head too well. So you might fire up a calculator and make use of this. Or instead, you might take the smart but lazy fashion to get to know how the debugger can work for you in this case. GDB is our preferred debugger, so I'll fire it up now. We haven't used it, but this will serve as your crash course on it. If I say GDB and then give a program, puzzle box over here, then this will initiate the program running under the auspices of GDB, the debugger, which will give me a chance to sort of stop and start the program at will. The basic interface to GDB, if I push enter at this point, is one that's a command line interface. And a lot of folks find this a little bit hard to reason about because it's less visual than it might be otherwise, but it is useful in some respects. I'm actually going to prefer something else instead, so I'll quit out of this one and pass one option, the text user interface, or TUI option, which will give me a somewhat different display in the terminal. If I punch enter this time, I might be prompted for a few things here, but eventually I'll get a screen that's divided between bottom side with the debugger command line active and top side with a source code display. Here you'll have to be a little careful because like up and down arrows will scroll source code up and down. Typing down here will put things down in the command box over there. And you'll want to then start learning some GDB commands that will serve you. For instance, the first thing that a lot of you will want to do is to specify what are the command line arguments to the runs of this puzzle box. The command to run the program is just run, but if I run it right now, let's see, I just have to say yes to this for a second. Then I'll get this little usage message indicating, oh, you need an input file for this thing. And that gets sort of tedious to specify every time. So let's set an input argument. Now notice the screen got a little bit messed up here. And so this is because the visual display over here doesn't account for any program output that comes out down here. And so you'll learn quickly the keystroke Control L. Pressing that will redraw the screen and sort of get you back into fighting shape up here. So let's set a command line argument so that when I run, the program knows to start reading from that input.txt. That'll be set args input.txt. Now, when I would run, you'll see output that looks more like what I got in the command line. Again, the screen tore up a bunch, but no matter there. Didn't give me much there, so you might sort of question the value of the debugger. Here's where the magic comes in. I can stop my program from running at any point that I choose. For this, you'll use a command that will set a breakpoint, break in this case. And I could say, for instance, break at phase 01. This is the function that I want to sort of interrogate those values that are coming in and what's done to them over here. If I run again now, instead of going all the way through, then there'll be a little bit of output set here. If I redraw the screen, you'll see time has stopped here at the beginning of phase 1. There are a few commands to start executing single source lines of code, for instance, next. And nicely, if I type next and then just press enter again, it'll repeat the last command so I can keep going. And so then there's printing commands. For instance, I can print out what is A. Well, it's 1 because that was read right out of the source file. Print B, that's 2. Print C, that's 3. Cool, so those are values over there. If I next one more time, and there are abbreviations in most cases, for instance, just N will be next as well, then I can see, here's my new value for A. Printed out with just P over here. It's 36. So I entered 1. And something was added on based on my hash, modulo 41 to this. It's apparently 35. I think to solve this, what I want then is for B to be bigger than 36. Okay, so maybe I would make it 40 or so. And then C would have to be less than that, but greater than A. So like 46 for B and 40 for C should do the trick. Now, this is a handy thing to know about. that if you happen to be working in VS Code or some other editor, then you can just go over to where you're not running the debugger and change the input.txt file. However, if you're working solely in the terminal, the keystroke Control Z will temporarily suspend the debugger or many other programs that you're working on. You can find out what programs are suspended by typing jobs. And you'll see I've got a couple of Vim instances running over here along with GDB. So let me bring into the foreground this Vim over here. If I were starting up the first time I touched Vim, but I already have it open, so I'll foreground it. And this little number over here is the job number. You can specify shorthand number 1 here. And this will bring me back into Vim. I have to remember, if I keep A here as 1, that was going to translate to 35. And so I said B should be, sorry, I'm going to undo that. To the end here. B I'd want to be, oh no. Oh, Vim. Let's see, B I'd want to be 40 and C 38. So I will write that into the outputs and suspend now. So I can recall, okay, what jobs do I have? I want to come back into GDB at this point. I foreground it. Oops, sorry, that brought back my own foreground number 3. So I'll bring me back to GDB over here. I'm about to, if I nexted right now, the current values I had for those will not satisfy this condition, and I'll get to the failure. What I need to do is to rerun the program at this stage, so it will reread from my input file what those new values are for A and B. The shorthand for that is run or just R, and this will honor then that input.txt as part of the command line arguments. Over here, a little bit of screen tearing as I printed. We're back over here. I don't really care to sort of next through a bunch of this stuff, so let me set a breakpoint here for line 264. So you can break at function names or individual line numbers over here, a bunch of ways to specify breakpoints. And if I punch enter at this stage, you'll see a little breakpoint that I haven't hit yet down here. And I can just continue executing until I get that by typing continue. That will execute up to the breakpoint over here. And what I want to check at this point is what's A, it's 36. What's B? It's 40, because that's what I put in there. What's C? That's 38. And if I next at this stage, I've made my way into the return, which is desirable. If I next now, then I'll be at the end of the function and pop back up into main, having earned some points over here. So I next this thing, then I'll get some points here, print out what my score is at the present, and we're good to go. 8 points in the bag. Now at this stage, I just might want to verify, so I'll suspend the debugger here and run puzzlebox myself with input.txt. And you can see phase 1 is passed. Phase 2 is complaining because it wants some more inputs, 4, 5, and 6, so apparently there are 3 inputs here. But my result so far is I have 30 points, or I'm sorry, 8 out of 50 points in the bag. So this gives you a basic flow. The next thing to do in the debugger would be to set a breakpoint at phase 2, modify input.txt to have some more inputs, and then start to figuring out what inputs are required to make it through phase 2 on that. You'll start to get pretty good and into a rhythm associated with GDB, and perhaps then get so familiar with it you might use it in other programs as you would seek to debug them. This is more or less an essential skill for computer scientists, and that'll prove so that as we get to the point of, for instance, writing assembly code, it's much harder to do print-style debugging in that with printfs, because just calling functions in assembly is a huge pain in the butt. And there, the debugger will be invaluable for sorting things out. Just a final word about this puzzlebox program. There are a bunch of different kinds of puzzles in there. And really all the make test prob 2 is going to do is to run the program to see how many points you earn. There are 60 points available in Puzzlebox, but only 50 are required to get full credits. And if you manage to solve all phases and get some of those, they'll be counted as makeup credits. This goes into your general pool of points for projects. And so if you lost some credit on project 1 or think you'll lose credit on subsequent projects, then this can be a great way to pad yourself so that you are resilient against that kind of loss of credit. It will not move your project score in the course overall above the allotted percentage, which is about 20%, but it will make sure that you get that full 20% if you accumulate enough makeup credit points there. That's all I got for you today. Sorry I went on a little bit long here, but all of you are watching this at double speed anyway, so it seems shorter anyway. As you have questions, put them up in Piazza, ask in office hours, and happy hacking to all of you.